In the heart of North America, hidden behind the picturesque landscapes of Yellowstone National Park, lies one of nature's most powerful forces, a supervolcano that could potentially alter the fate of an entire continent. Volcanoes around the world have repeatedly demonstrated their destructive power, but Yellowstone is unique. Its eruptions occur with such force that they can impact the global climate and the life cycles of the planet. Every tremor of the earth, every burst of steam raises questions. Is the moment of a new awakening approaching? Is the park ready to unleash its volcanic power once again? And most importantly, are we prepared for what that might mean? Seismic activity in Yellowstone National Park is one of the key phenomena closely monitored by scientists around the world. A recent powerful geothermal explosion that occurred on July 25, 2024, caused panic among tourists when a mixture of rocks, steam, and mud erupted near the Old Faithful geyser. This event has drawn the attention of researchers studying its causes and potential consequences. The explosion, which took place at 10 a.m., resulted from the blockage of natural water tunnels beneath the park, leading to increased temperature and pressure, ultimately culminating in the explosion. Experts like volcanologist Michael Poland emphasize that such cataclysms may indicate rising activity of the supervolcano located in Yellowstone. The largest hydrothermal explosion crater in the world, situated here, has a diameter of 2.4 kilometers, underscoring the seriousness of the processes occurring. Professor of Geology Bill McGuire, who is monitoring the situation in Yellowstone, asserts that America is sitting on a powder keg. Satellite imagery and crustal movement data indicate active processes beneath the Earth's surface, while temperatures in Yellowstone are 30 to 40 times higher than in the rest of the continent. Following the explosion, tourists began to leave the park in a panic, and rangers closed some areas for safety. Despite no reports of injuries, the incident sparked a wave of rumors and concerns in the community. Park authorities are trying to reassure the public by referencing similar events that have occurred in the past. However, this does not alleviate the tension. Scientists warn of the potential catastrophic consequences of a supervolcano eruption. The worst-case scenario involves an explosion equivalent to 1,000 atomic bombs, which would lead to the formation of a massive crater and an ecological disaster. According to Yakov Levenstern from the Yellowstone Volcanic Observatory, previous eruptions of the supervolcano expelled more than 1,000 cubic kilometers of magma, which could cover North America with up to 30 centimeters of ash and cause a global temperature drop. Professor McGuire cautions about the seriousness of the situation, pointing to active processes beneath Yellowstone and the potential threats to the entire world. Bulgarian clairvoyant Vanga also predicted that part of the US would be submerged, while volcanoes would awaken elsewhere, including the Yellowstone supervolcano. A recently surfaced prediction from an individual claiming to be a time traveler adds further anxiety. He asserts that thousands of Americans will die due to a major eruption. The question of whether such seismic activity can herald larger catastrophic events remains open. Earthquakes in highly active volcanic zones often indicate changes deep within the Earth, but do they always signal an impending disaster? How is this activity connected to the magmatic system hidden beneath the park? And what could this mean for the future of Yellowstone and its supervolcano? Yellowstone is the very supervolcano that gained fame due to the 2012 film. The Yellowstone caldera, located in the national park of the same name in the United States, is a volcanic caldera situated in the northwest corner of Wyoming, which occupies most of the park. The caldera measures approximately 55 by 72 kilometers, a size determined through geological surveys conducted by Bob Christensen of the U.S. Geological Survey in the 1960s and 1970s. Yellowstone is located above an area known as a hotspot, where molten mantle rock is moving toward the surface. This hotspot covers the Yellowstone Plateau and is the source of volcanic activity in the region. The uniqueness of the Yellowstone volcano lies in two key factors. First, its size is such that it does not form a typical volcanic cone. Instead, during an eruption, The upper part of the volcano simply collapses into a vast cavity, creating a caldera that in the case of Yellowstone reaches dimensions of 55 by 75 kilometers. Second, this volcano is not located at a tectonic plate boundary, but is situated right in the middle of the North American plate. Its eruptions are caused by a mysterious and poorly understood hotspot located beneath the tectonic plate. Supervolcanoes are among the most destructive forces on our planet, with eruptions that can be tens of times more powerful than those of ordinary volcanoes. While they can lie dormant for hundreds of thousands of years, magma remains trapped in vast reservoirs within their vents. However, when an eruption occurs, this magma erupts to the surface with apocalyptic force, capable of destroying entire continents. The first of 3 massive eruptions of the Yellowstone supervolcano occurred 2.1 million years ago, leading to the formation of the Island Park caldera and the Huckleberry Ridge tuff deposits. The approximate size of the caldera is 80 x 65 kilometers, making it one of the largest in the world. As a result of this eruption, mountain ranges collapsed, and ejecta rose to heights of 50 kilometers, reaching the upper boundary of the stratosphere. Volcanic ash covered more than a quarter of North America. This cataclysm can be compared to the eruption of the Toba supervolcano about 75,000 years ago, which expelled around 2,800 cubic kilometers of magma. The second eruption took place 1.3 million years ago, with an output of 280 cubic kilometers, resulting in the formation of the Henry's Fork caldera. It is a very large caldera, measuring 29 x 37 kilometers, and its curved edges are visible from many locations in the Island Park area. The third eruption occurred 640,000 years ago and was half as powerful as the first. This eruption created a caldera, an enormous circular depression with a circumference of 150 kilometers, as well as the Lava Creek tuff deposits. For the past 17 million years, the Yellowstone hotspot has produced continuous intense eruptions, including less powerful eruptions of basaltic lava. These eruptions contributed to the formation of the eastern part of the Snake River Plain from what was once a mountainous region. At least a dozen such eruptions have been so massive that they can be classified as super eruptions. A volcanic eruption can sometimes lead to the depletion of an underground magma reservoir, magma chamber, which can in turn cause the collapse of the rock above it and the formation of a geological depression known as a caldera. The oldest discovered remnant of a caldera is located on the border of Nevada and Oregon, near McDermott. Younger caldera remnants can be found in an area stretching from the Nevada-Oregon border through the eastern Snake River Plain to the Yellowstone Plateau. One such caldera is the Bruneau-Jarbidge caldera in southern Idaho, which formed 10 to 12 million years ago. As a result of this phenomenon, ash was ejected over a distance of 1,600 kilometers toward northeastern Nebraska, leading to the demise of large herds of rhinoceroses, camels, and other animals in what is now the Ashfall Fossil Beds State Historical Park. Over the last 17 million years, there have been 142 or more eruptions from the Yellowstone hotspot that have formed the caldera. This phenomenon remains one of nature's most unpredictable threats. What other geological signs might indicate increasing pressure in the park's magma system? One of the most notable features of Yellowstone National Park, alongside its hidden supervolcano, is its geysers and hot springs. The park is home to about 3,000 geysers, which is approximately 2/3 of the total number of geysers on the planet. Among them stands the world's largest geyser, Steamboat, which erupts up to 300 feet, 91 meters high, and the famous Old Faithful geyser, which shoots jets of hot water over 40 meters high at intervals of 45 to 125 minutes, with the most frequent eruptions occurring approximately every 90 minutes. Due to its predictability, Old Faithful has become particularly popular among tourists. In addition to geysers, Yellowstone contains around 10,000 different geothermal features, including hot springs, fumaroles, mud pots, and more. This number accounts for half of all geothermal features in the world. In May 2001, the Yellowstone Volcano Observatory was established, primarily to monitor volcanic and geothermal activity, while also assessing the potential hazards associated with this activity. In 2003, Access to the Norris Geyser Basin was restricted for tourists due to recorded increased activity and abnormally high water temperatures in some geysers. Several geysers became so hot that they began emitting steam instead of water. Research also revealed an unknown cone on the bottom of Yellowstone Lake, which, although not an immediate eruption threat, piqued the interest of scientists. In 2004, 5 bison died in the Norris Basin from geothermal gases, further drawing attention to safety concerns. By 2006, it was noted that the ground in 2 locations within the park was rising at a rate of 6 centimeters per year, which attracted increased media attention to the volcanic and geothermal activity in the area. Can such regular manifestations of hydrothermal activity be considered a reassuring sign of stress relief, or are they signals of gradually increasing pressure beneath the surface? And how is hydrothermal activity related to the magmatic processes that fuel this volcanic region? Geothermal activity in Yellowstone National Park is a manifestation of colossal processes occurring beneath the surface. It is driven by a powerful magma chamber that heats underground water, creating conditions for the formation of geysers, hot springs, and mud pots. Yellowstone is a plateau high in the Rocky Mountains, covered in snow for more than 6 months a year. The average annual temperature is 2.2 degrees Celsius, just above the freezing point of water. However, Yellowstone is also an active geothermal zone with hot springs averaging around 92 degrees Celsius, the boiling point of water at Yellowstone's average elevation, and steam vents that reach temperatures of 135 degrees Celsius. Only about 0.3% of the park's area consists of thermal soils. In some thermal zones of Yellowstone, the heat flow exceeds 100 watts per square meter, which is approximately 50 times greater than Yellowstone's average and about 2,000 times greater than the North American average. This immense heat flow originates from molten rock or magma in the crust beneath the caldera, ultimately generated by the Yellowstone hotspot, a partially molten region of the Earth's mantle, hundreds of kilometers beneath the surface. How is heat released in Yellowstone? Heat from the Earth is released in Yellowstone through 2 main processes: conduction and convection. Conduction is the transfer of heat from a hotter material to a cooler one. A typical example of conduction is the transfer of heat from the plate through the bottom of a coffee pot to the liquid inside. In Yellowstone, conduction helps transfer heat from deep within the Earth to shallower depths. Of the heat released by the Earth in Yellowstone, about 25% is dissipated through conduction. Convection is the heat carried by moving hot material, such as hot water or magma. Convection occurs inside a coffee pot when heat is transferred upward through the liquid as hot water rises from the heated bottom, being less dense than the cooler water above. When water boils, the upward movement of hotter water and the compensating downward flow of cooler water create what is known as a convection cell. The convection of molten rock helps transfer heat upward through the Yellowstone caldera. Near the surface, the convection of hot groundwater drives geysers, hot springs, and fumaroles. Convection accounts for approximately 75% of the heat released by the Earth in Yellowstone. Can we use this heat for energy production? While Yellowstone and its surroundings represent a significant geothermal resource, the park itself is closed to development. Because geothermal development often leads to a decrease in the flow of nearby hot springs and other geothermal features, it is unlikely that anyone would receive permission to develop geothermal energy in the region outside the park. In the United States, there are other natural heat sources that are used for geothermal energy. Typically, hot water or steam is extracted from a deep reservoir through a geothermal well. The fluid is then expanded through a turbine to generate electricity. In California, power plants such as the geysers, Salton Sea, Coso, and Casa Diablo, among other geothermal systems, generate about 4 or 5 gigawatts of electricity. This is enough to power several million people. How might deep geothermal processes impact the biodiversity existing in such extreme conditions? The biodiversity of Yellowstone National Park is a unique phenomenon closely linked to the geothermal activity occurring in the region. In conditions of extreme temperatures and specific water chemistry, live organisms thrive that can survive where other life forms perish. Among the most remarkable representatives of this biodiversity are thermophiles, microorganisms capable of existing at temperatures exceeding 45 degrees Celsius. These organisms play a crucial role in the park's ecosystem and demonstrate an astonishing ability to adapt to conditions that seem entirely inhospitable to life. One reason for the survival of thermophiles is their possession of enzymes that can function at high temperatures. They are divided into two main groups, obligate and facultative. Obligate thermophiles require a constant maintenance of high temperatures for their growth. In contrast, facultative thermophiles can adapt and grow at both high temperatures and lower ones, such as below 50 degrees Celsius. Within this group, hyperthermophiles are identified as a subgroup of extreme thermophiles, for whom optimal growth temperatures exceed 80 degrees Celsius. Studying these organisms opens new horizons for scientists in understanding the limits of life on Earth. Thermophiles not only represent an interesting subject for biological research, but can also aid in the search for extraterrestrial life. What else do we know about the organisms in this park? What is the significance of preserving unique ecosystems in modern times, when each generation faces the threats of climate change and environmental degradation? The park is also home to around 2,000 species of plants and several hundred species of mammals, birds, reptiles, and fish, including species that are endangered. Much of the park's area is covered by forests, while a smaller portion consists of grasslands. Every year, wildfires occur in this area, with about a third of all forests having burned as a result of the catastrophic fires in 1988. Could future changes in the magmatic system, perhaps triggered by increasing seismic activity, impact this fragile biodiversity? The historical significance of Yellowstone National Park is immense, as it not only became the first national park in the world, but also a site where important cultural and historical aspects converge. For centuries, this region has been home to many indigenous peoples, such as the Shoshone, Crow, and Lakota, who utilized the park's natural resources for their livelihoods and cultural practices. For these peoples, Yellowstone held not only utilitarian value but also spiritual significance. They regarded this land as sacred, and many local legends and myths were connected to its geothermal features. The discovery of Yellowstone by European explorers, culminating in its establishment on March 1, 1872, marked a new chapter in its history. The Washburn expedition of 1870 explored the northwestern region of Wyoming. Led by Henry Washburn and Nathaniel P. Langford, along with a U.S. Army escort headed by Lieutenant Gustavus C. Doane, the expedition followed a general route and became the first documented attempt to explore and describe this remarkable area. During their research, the expedition members created detailed maps and observations of the Yellowstone region. They examined numerous lakes, climbed several mountains, and observed wildlife. The expedition visited both the upper and lower geyser basins. One member of the expedition, writer and lawyer Cornelius Hedges from Montana, later wrote a series of articles for a newspaper in Helena, Montana, describing his experiences. In his discussions with other group members and in his newspaper articles, Hedges actively advocated for the designation of the Yellowstone region as a national park. This idea was originally proposed by former acting governor of Montana, Thomas Francis Maher. How can science and technology assist in predicting natural disasters, and how effective are current monitoring systems? Can they truly protect both nature and the people living in this unique yet hazardous region? Scientific monitoring of Yellowstone National Park is a complex and multifaceted system aimed at studying and predicting seismic activity and volcanic processes. Scientists utilize modern technologies such as seismographs, GPS stations, and satellite data to monitor changes in the Earth's crust and the park's magmatic system. These tools not only track the current state of activity, but also reveal long-term trends that may indicate increasing risks. Seismographs play a crucial role in the monitoring system by detecting even the slightest vibrations in the Earth's crust. The data obtained from seismographs are analyzed to determine the location, depth, and magnitude of earthquakes. GPS stations installed throughout the park provide information on crustal movement and changes in topography. These stations can detect even minor shifts, allowing for the prediction of potentially hazardous situations. Satellite data, in turn, helps track changes in surface temperature and composition, which may indicate increased activity of hot springs and geysers. These monitoring technologies and methods not only enhance safety for visitors and local residents, but also play an important role in educational initiatives. The information collected by scientists is shared with the public and educational institutions, raising awareness of geological risks and the need to protect the environment. Nevertheless, despite advancements in monitoring, is it possible to fully predict and prevent natural disasters? What new technologies could be developed to enhance forecasting accuracy and protect Yellowstone's unique ecosystem? Computer modeling plays a crucial role in studying the geological processes occurring in Yellowstone National Park. These complex simulations allow scientists to investigate the dynamics of volcanic activity and seismic phenomena based on extensive data collected using modern monitoring technologies. By employing mathematical models, researchers can simulate various scenarios, including potential earthquakes and eruptions, as well as assess their possible consequences for the ecosystem and the local population. For example, the author of the Yellowstone volcano study, Lijun Liu, a geodynamicist from the University of Illinois at Urbana-Champaign, reached the following conclusion through computer modeling. The simulation results indicate that the movement of fragments of the ancient Farallon plate may have disrupted the normal functioning of the mantle, thereby contributing to the replenishment of the Yellowstone volcano. However, how reliable are these computer models in predicting future natural disasters? And how can modeling-based research influence approaches to education and public awareness regarding the risks associated with volcanic activity and seismic events? The question of the reality of the threat of a volcanic eruption in Yellowstone National Park remains open. It is difficult to accurately determine the processes occurring within it. Many scientists consider the likelihood of an eruption to be low, but NASA has developed a strategy to prevent a potential catastrophe. The main idea is to inject water into the volcano before it poses a real danger. However, implementing this plan presents certain challenges and high costs. According to Brian Wilcox from NASA's Jet Propulsion Laboratory, using large volumes of water to cool the volcano is contentious, as there are regions of the world where water is critically scarce. The most effective solution to the problem may involve drilling 2 holes on either side of the volcano to inject water under high pressure. This would gradually lower the temperature of the magma. However, creating an opening at the top of the magma chamber could, on the contrary, trigger an eruption, and there is no guarantee that the proposed measures would have a long-term effect. Nevertheless, NASA scientists hope that their plan will serve as an impetus for other experts in the search for new ways to prevent potential hazards associated with volcanic activity. Subscribe to our channel and stay updated to not miss the latest news and exciting updates about Yellowstone National Park.